Hello! In this first lecture, we'll take a look at our place in the universe and try to wrap our minds around the sizes of our planet, our solar system, our galaxy, and our universe. The backdrop here is an image that was taken with the Hubble Space Telescope. It's a very small piece of sky. Imagine taking a picture through a 1 millimeter by 1 millimeter square held at a meter away, and that's what we have here. But even with such a small field of view, look at all those galaxies. The whole image contains about 10,000 galaxies, and each individual galaxy contains billions of stars. The smaller smudges are galaxies so far away that the light takes billions of years to reach Earth. The only objects that aren't galaxies are a few stars in the foreground. These stars are part of our own Milky Way Galaxy. The study of astronomy can be likened to a grand journey, and like most journeys, we'll begin from home. Home for us is planet Earth, the third of 8 planets in our solar system. Earth is on average 93 million miles, or about 150 million kilometers, from the Sun. At highway speeds, it would take about 152 years to travel from the Earth to the Sun. Our solar system consists of the Sun, the planets and their satellites, and many other smaller objects such as asteroids and comets. The 8 planets are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. There are many mnemonics for remembering the planets. The one I learned when I was a young sprout is Mary's velvet eyes make John stay up nights. You've probably heard that Pluto is no longer considered a planet, and this is why. The definition of planet was set in Prague in 2006 by the International Astronomical Union. They say that in the solar system, a planet is a celestial body which is in orbit around the Sun, has sufficient mass to assume a nearly round shape, and has cleared the neighborhood around its orbit. Pluto fails on number 3. It's just too small. There are objects besides the Sun and planets in our solar system, like the millions of asteroids or minor planets. Most are thought to be the shattered remnants of planetesimals, bodies within the young Sun's solar nebula that never grew large enough to become planets. Comets are essentially dirty snowballs made of rock, dust, water ice, and frozen gases like carbon dioxide, carbon monoxide, methane, and ammonia. Determining their size is difficult, but comet nuclei with radii up to 20 kilometers have been observed. The tail of a comet can be much larger, thousands or even millions of kilometers across. The orbits of comets are highly elliptical. That is, their orbits look like really squished ovals. Periodically, Earth will pass through a comet's orbital path. Because comets leave all sorts of rocky debris behind them, when Earth passes through a comet's orbit, the debris hit our planet. You may have seen shooting stars in the night sky. These are meteors, little comet pieces burning up in our atmosphere. Therefore, when we pass through a comet's orbit, we get a meteor shower. The Sun is our parent star and the source of light and life on planet Earth. As far as stars go, the Sun is nothing exceptional. It formed approximately 4.5 billion years ago and will continue to provide energy via nuclear fusion in its core for another 5 billion years or so. All the other stars we see are not really different from the Sun. Our parent star is just one of several 100 billion stars in our galaxy, the Milky Way Galaxy. The sky is divided up into 88 official constellations defined by the International Astronomical Union. Every star in the sky belongs to a constellation. From a dark sky site, you may notice a cloud-like band of light arching overhead. It may be difficult to tell with just your eye, but binoculars or a small telescope will show that this band of light is the result of many stars that appear close together. This is the view we have of our galaxy, the Milky Way. Unfortunately, the band of the Milky Way is nearly impossible to see from Rockville or DC unless all of the power goes out. And it may seem strange that we see a band of light like this, but once you think about how we're situated inside the galaxy, it should make a little more sense. The Milky Way resembles a thin circular disk, like a pancake. Our solar system is inside the disk of the galaxy, about 2/3 of the way out from the center. If we look straight up or straight down, we don't see as much of the pancake compared to when we look into the pancake. That is, when we look in the direction of our galaxy's disk, we see many more stars, the band of the Milky Way, than when we look in directions above or below the disk. Every star you see in the night sky is part of our Milky Way galaxy. There are billions of other galaxies with billions of stars all their own. We can see a few of our neighboring galaxies from a dark sky site with the naked eye. They look like fuzzy cotton balls, but we cannot distinguish the individual stars in any galaxy with our eyes, except our own. Each galaxy can be thought of as an island of stars. If you lived in another galaxy, you would see a whole new set of stars in your sky. Within the disk of the Milky Way are clouds of dust and gas called nebulae, like the beautiful Orion Nebula. Nebulae can be enormous compared to the size of our solar system, but small relative to the total size of our galaxy. There are billions of galaxies in the universe, and galaxies tend to group together. Our Milky Way, for example, is one of 2 large galaxies amongst about 40 galaxies in what is known as the local group. Groups of galaxies with more than a dozen members are known as galaxy clusters, like the Coma cluster shown here. This is an image of our neighboring galaxy, the Andromeda Galaxy, also part of the local group. On a very large scale, the universe has structure. Galaxies and galaxy clusters appear to be arranged in sheets and chains with large voids of emptiness between them. The superclusters are where galaxies are clumped together. Everywhere we look in the universe, we see this overall structure. Later in the semester, we'll talk more about the large-scale structure of our universe. This is cosmology. All right, now let's take a moment to talk about units of distance. There are a variety of units that are used for measuring distance, but there are 2 that are often used in astronomy. The first is the astronomical unit, or AU. The astronomical unit is Earth's average distance from the sun, and it's about 150 million kilometers, or 93 million miles. The AU is useful for smaller measurements. For larger scales, we generally use the light year. A light year is the distance that light can travel in 1 year. Light is pretty darn fast, so it can cover a lot of space in a year. A light year amounts to 10 trillion kilometers, or about 6 trillion miles. It's important to remember that a light year is a measure of distance, not time. Also, nothing travels faster than light. It's the universal speed limit, and it's a constant. The speed of light is 300,000 kilometers per second. Because it's a special number, it gets its own special letter. The speed of light is denoted by the letter C. The C stands for celeritas, which is Latin for rapid or swift. Light has a finite speed, so it means it takes a certain amount of time for light to travel from an object to us. Even for close objects, you never see anything in real time. Consider the moon. It takes light from the moon 1 second to reach us on Earth. It takes light from the sun about 8 minutes to reach us. This means if something really strange happened right at this moment on the sun, we would not know about it for 8 minutes. Sirius is a nearby star. It takes 8.6 years for the light to reach us from Sirius. Light from the Andromeda Galaxy spends 2.5 million years traveling to reach Earth. This means we see objects as they were in the past, and the farther away we look in distance, the further back we look in time. Here is the lovely Andromeda Galaxy again. The Andromeda Galaxy is actually bright enough that you can see it with your naked eye from a dark sky site. It looks a little bit like a fuzzy cotton ball. From Rockville or anywhere with city lights, we need binoculars or a telescope to see it. If you could go out tonight and see the Andromeda Galaxy, the light that would hit your eye left that galaxy 2.5 million years ago. When will we be able to see the Andromeda Galaxy as it looks right now at this very moment? Well, we have to wait 2.5 million years. We estimate that the universe is about 14 billion years old, and we'll talk all about how we know this later in the semester. Because of the finite speed of light, the farther away something is, the longer it took the light to reach us. At great distances, we see objects as they were when the universe was younger. The observable universe is the portion of the entire universe that we could potentially observe. If we tried to look beyond 14 billion light years, we'd be looking to a time more than 14 billion years ago. And this is before the universe existed, so there's nothing for us to see. The distance of 14 billion light years therefore marks the boundary or horizon of the observable universe. And the observable universe is that portion of the entire universe that we could potentially observe. Finally, let's take a brief look at the history of our universe. Observations of distant galaxies outside of our local group reveal that they are moving away from us. We also find that the farther away a galaxy is, the faster it is moving away from us. These observations imply that the space between galaxies is increasing with time. The universe is expanding. Following this line of thought, we can figure that galaxies must have been closer together in the past. If we go back far enough, we must reach the point at which this expansion began. We call the beginning of the universe the Big Bang. Astronomers use the observed rate of expansion to calculate that the Big Bang occurred about 14 billion years ago. The universe as a whole has continued to expand ever since the Big Bang, but on smaller scales, gravity holds things together. The stars within galaxies and galaxy clusters do not expand. Things on Earth, people, rulers, coffee cups, are not expanding. It's only the space between galaxies that is expanding. Let's go back to our galaxy for a moment. The disk of the galaxy is where all star formation takes place, simply because that's where the material is to make new stars. We'll talk much more about this later in the semester, but for now know that a star goes through most of its life generating energy via nuclear fusion reactions in its core. Eventually, every star will run out of nuclear material. The largest stars use their nuclear fuel the quickest and die in massive explosions called supernovae. When a star dies, it blows its atmosphere back into space. Eventually, this material will form new stars. Our sun and solar system were created from the remains of other stars. Every atom on Earth was once part of a star. From the iron in your blood to the calcium in your bones, every bit of you was once inside of a star. The late astronomer Carl Sagan was fond of saying, "We are all stardust." It's true. We are made of the universe. We are a cosmic consciousness. We are truly a way for the universe to know itself. That's all for the first lecture. Over the course of the semester, we'll explore details of the topics I touched on today, as well as many other fascinating things like light and telescopes and exoplanets and dark matter. But for now, take care, and I'll talk to you again soon.